Hello, it's Keith here, and this is lesson 4 of the platform-specific series of my Z80 assembly tutorials. Now, last week we had a look at how to get bitmap graphics to the screen on the Amstrad CPC and the Enterprise, and we were getting two forms of data to the screen. One was a platform-specific bitmap, which had to be encoded in the correct format for that system screen, and the other was a platform-independent 1 bit per pixel bitmap, where we were going to use this to get a font to the screen in a common way on all the systems. So we're going to continue from last week, and this week we're going to have a look at how to do that on the SAM Coupe, which is a 16 color system, so 4 bits per pixel, and also on the ZX Spectrum, which essentially is a 1 bit per pixel system but allows to set a color attribute for every 8 by 8 pixel square. So okay, well, let's make a start of those systems. So first, I'll just point you to the example code here. It's the same code as last week. One thing I do need to add to last week's is we can't set the color data on the ZX Spectrum in a way that is the same on the other systems because it just doesn't work the same. So what we're going to do is we're going to get a location in the same format as our normal get screen pos bitmap function, but this time we're going to get a location in the color data. As I say, each square, like this A here, can only have one color attribute, and it covers 8 pixels across and 8 pixels down. So this get colmempos will get a single byte location, which we can then set the color that we want that location to be. So you can see here I've set this letter A to blue. Okay. Anyway, let's make a start on the ZX Spectrum then, and let's have a look at what it actually takes to get the data to the screen. So you can see at the top here, we've got our bitmap, and it's probably more logical than the other ones because the ZX Spectrum is essentially just a black and white system, so there's only 1 bit per pixel. So let's have a look. So the first thing we'll have a look at is this here, the header information. It's very simple on the ZX Spectrum. The data we're putting to the screen, whether it's the font data or the bitmap data, is just 1 bit per pixel. So we just put the bytes straight to the screen. The screen is byte aligned, so if we're just moving across the screen and not down, we only need to ink L. And that's it. Things are a little bit more tricky when it comes to getting the screen memory positions, but not too much. It's essentially the same on the Spectrum, just like on the CPC. The screen memory is addressed within the system memory. It's not an external device of any kind like it is on some of the other systems we're going to look at. But all we need to do is, in the same way as before, we get the starting address of the line, and then we add the X offset and any alternate screen banking to that line offset, and that gives us the correct location of the row column pixel that we want to change, and that's all there is to it. Now, get next line is quite tricky. Screen memory positions on the Spectrum are kind of split into sections, and I think this comes down to making it easy to move around the screen bytes in an 8 by 8 grid for drawing fonts that are aligned to an 8 by 8 grid, but it unfortunately makes it quite difficult if you need to move down the screen in a continuous fashion, irrespective of wherever you are. So when you're accessing the ZX Spectrum screen, you'll have a HL memory address, and if you look at it in bits, then the first 5 bits will be the X position, and that's why we only need to do an ink L when we're moving across the screen. But when we're moving down the screen, we unfortunately have a little bit of a tricky case on it. So if we were at the very top of the screen, for the first 7 times we move down, we would only need to do an ink H, and you can see that's represented here. But when that overflows, we then need to start inking the top part of L, these 3 bytes here, and that's this bit here. But then when that overflows, we then need to start inking these 2 bytes here. And as I say, I think this is really, I may be wrong, but I suspect this really comes down to making it easy to move across the screen by just inking L, making it easy to move down the screen by just increasing H within 1 character block. But then unfortunately it does make it quite tricky to move beyond that 8 character block. But you know, it's not too bad. And then these bytes here are the screen memory location, because the screen base is at 4000. You can have a second screen if you're doing screen buffering, which we will be looking at later, and that would start at C, which would be effectively setting bit 7 to 1. But that's the screen memory locations. I say they are a bit of a pain, but honestly, you can just use this code as it is. I think I found it originally on a website somewhere and just made a slight change on it, but it say basically it's not too much. There's not really any optimization you can do beyond what's here. So if you don't understand it, don't worry. Just copy what's here and use it, and it will work absolutely fine for you. So here's the table, which I created in the same way as with the Amstrad CPC ones. If you didn't see last week's tutorial, I would suggest you watch it if you have time, because even though it's Amstrad CPC specific, there is some interesting things in there. And as I say, all of these systems are very similar. So if you're just reinforcing what you've seen in this lesson by watching that, I think if you've got the time, it's probably worth it. So spleen initialization, we don't have to do any on the ZX Spectrum. The ZX Spectrum basically only has one screen mode, so there's no text and graphics mode, there's no different resolutions, so no initialization required. Now, as I say, when you're just putting data to this area here from 4000 to 5800, that's just black and white bitmap data. But when you're altering the color information, you're accessing a range from 5800 to 5AFF, and that's where the color information for the screen is held. And it's actually in a linear format. So the first byte is the top left here, and then you would move along 32 bytes across, and then you would end up on the next line down. So there's no weird interlacing effect that you have to deal with. It's very simple to work out, and it's very simple to move across the screen and fill the color in. But you do have to sort of understand the layout a little bit to get the screen memory location, and you do have to work within the rather tricky limitations of the ZX Spectrum's color system, which I'll just explain for you now. I mean, for me, the Amstrad CPC reminds me of the old teletext systems you used to see. I don't know if it's literally identical, but it's certainly quite similar. It's basically a system which has 8 colors, which you can see here. Color 0 is black, color 1 is blue, color 2 is red, and all the way up to white. Now you can set the background color from 0 to 7, and you can set the foreground color from 0 to 7. And then you have 2 other options, and these affect both the background and foreground colors if you set them. There is a flashing option, which will make it flash on and off. Honestly, not very useful for gaming, but it's there. And then there's the bright option. Now, what this does is it increases the brightness of both the background and the foreground simultaneously. And generally speaking, you're going to want to use the bright option, because for most of the things you're going to be seeing, that's going to be what people are going to expect. The dark blue, for example, is almost so dark you can hardly see it. Now, actually, that said, this grey here is actually dark white, so possibly not being entirely truthful there. There is no such thing as bright black, by the way. Dark black and bright black are the same thing, and that's a reason why you will quite probably want to work with the Spectrum with a black background. Now, luckily Chibi Akuma's already did that, but if you were trying to make a game with a magenta background, dark, you would be limited in the ways you could use the dark magenta option, because it would look quite striking if you were using that. As if it's not been made clear already, if this letter A was moving 1 pixel at a time across the screen, it's not possible to move those colours 1 pixel at a time across the screen. There's no way of shifting the overlay or any more advanced way of doing the colours. The colours are always limited to an 8 by 8 pixel square, and it's aligned to the character drawing, so there's not much you can do there. And if you watch Chibi Akuma's on most games on the ZX Spectrum, you will find that either they move in the way Chibi Akuma's does. The sprites tend to move 1 8 by 8 block at a time, so you will never see a sprite move 4 pixels across. It will always move 8 pixels across or 8 pixels down, and that allows me to keep the color information matching up to the sprite. Or if you look at Chibiko in my game, the main character, as she moves up the screen slowly, you'll see the colors don't line up correctly with the face and hair anymore, and that's because of the limitations of the ZX Spectrum. But you just have to accept those. That's what they are. You can either you accept the limitation and make everything black and white, or accept the limitation and make the colours not match the sprites, or move the sprites 8 pixels at a time in both directions. But that's your only options. So anyway, if you're not sure on this, have a play with it. But if you want to set colours and keep it clear in your code, you can do this here. And what I've done is I've selected colour 1 for the background, and I just multiply that by 8 to turn it into a background color, because 8 is bit 3, and that's the first of the background colors. And then I just add the foreground color here, which is white, which is number 7, and then I add 64, which is bit 6, which makes it all bright. Now if I took that 64 out and recompiled, it would make it dark. So let's just prove that. Let's actually go a little bit further, why don't we? Let's make the foreground yellow and the background red as well, why not? And so now you can see the text has changed to a kind of dark yellow because I removed the bright bit, and the background has changed to dark red. As I said before, it's not possible to have bright yellow and dark red. That's a real big limitation. It took me a while to get my head around that. When I was brainstorming things, I kept forgetting that the limitation applied to both simultaneously. So there you go. That's the limitations of the Spectrum graphics. So it's not too much to worry about here, really. Very simple, very straightforward. Let's move on to the Sam Coupe. Now, compared to the ZX Spectrum, the Sam Coupe really does have some incredible abilities. Well, to be honest, compared to even the Amstrad CPC, the screen is 256 by 192, but it's 16 colours and there's no colour limitations. The Sam Coupe does actually have a ZX Spectrum emulation mode, which does the exact same screen settings as ZX Spectrum, but I think you're probably going to want to avoid those, so we're not going to cover them in this lesson. So let's have a look. So when it comes to getting data onto the screen is aligned horizontally and vertically. So if you move to the far right byte of the top line and increase by 1 byte, you arrive at the immediately lower line, which means that, like on the Enterprise, we have a very easy job moving across the screen and a much easier job than the Amstrad CPC moving down it. And we'll have a look at that later. So here's our command to get the next byte very easily. Loading information in is just the same as on the other systems. We just load the byte into the current screen memory. Now, because it's a 16 color system, every byte will only contain 2 pixels worth of information, and it's just going to be those tiny 2 dots there. It's a very high resolution screen compared to the Amstrad CPC 16 color. Now, the pixel information is not split in the same way as the Amstrad CPC works. On 16 color mode, it's actually the same way as the MSX works, where the left foremost bits are the leftmost color and the right foremost bits are the rightmost color. So it works quite differently to the Amstrad CPC, and it's, to be honest, the more logical way for me. But again, with the Amstrad CPC, we do have to split our black and white bitmap into 4 chunks, shift the bits accordingly, and then put them on the screen. But that's no problem. Now, what is a much bigger problem on the Sam Coupe, and what's kind of forcing me to teach something a little bit earlier than I really want to, the Sam Coupe, because it's a 16 color screen and it's 256 pixels by 192 pixels, it's actually a 24 kilobyte screen memory compared to the 16 kilobytes of the Amstrad CPC and the 8 kilobytes of the ZX Spectrum. Now, the problem this leaves us is it's actually using over a quarter of the memory of the Sam Coupe, and even worse, and possibly related, the Sam Coupe, unlike the other systems we're looking at, when you want to switch in the extra memory, and the Sam Coupe has 256K of memory minimum, so it has a lot, but when you want to switch it in, you effectively have to switch it in 32K chunks, so you have to switch half of the memory map in one go. Now, in our program, all of these examples start at 8,000 in memory address. Now, because the screen memory is so big, we can't really page it in at the top half of the screen of the accessible memory range. So we're actually paging it into the bottom from 0000 upwards to 6,000. That's where we're putting it in. But of course, that poses some quite serious problems with regards to interrupt handling, because the interrupt handler would call to 0038. So what we've got to do in this example, it's only a basic example, so what we've got to do is we've got to disable interrupts when we're doing our screen work, and this example here has interrupts disabled the whole time. Now, so what we need to do to actually use these examples is we need to page out the ROM, which would usually be in the first 16 kilobytes of memory, load RAM into that area, set the system to use that screen RAM, and then start drawing on it. Now, what I've done is I've provided 2 sample functions here, one called start drawing and one called stop drawing. Now, start drawing will turn off the ROM at that lower address, so you can start doing your work and drawing data to the screen. And then stop drawing will turn the ROM back on again in case you need to use the firmware functions. Now, that's not something we're actually planning to do very much here, and in these examples we'll actually be using RST mode 2 to avoid this problem. But if you were writing your own game in depth and you wanted to use RST1, well, you've got 2 options. Either turn off the interrupt while you're doing your screen drawing and then page the ROM back in or your RAM back in, or alternatively reorganize your code so that the game code is is below 8,000, and then page the entire top bank into that screen memory instead. Either way is going to cause you problems, but it's just you've got no choice when you've got a huge 24 kilobyte screen and a system that's designed around 32K page banking chunks. So there we go. I'm going to cover page memory banking in more detail on all the systems later, but just as a quick taster, here's the sort of layout of the memory address, and we send the data to port 250 to define it, and so this bit 1 here turns off the ROM, and this bit 0 here turns it back on, and that's the chosen bank here. So yeah, that's a very quick introduction. We'll go over it later, but really if you just want to play around with it, just use this example as it is, and hopefully that'll get you started. And by the time you're looking to do more advanced things, I will hope I will have better tutorials here covering memory banking better for you. So that's the basics of moving around the screen. Getting screen memory locations is exactly the same as on the other systems, to be honest. We've got our bank of memory addresses here, and then we're just adding our screen location, which is based at 0, and then we're just adding the X position again. It's almost exactly the same as all the other systems. It's only when it comes to the MSX and the TI 83, which we'll be covering next week, where things become quite different. So the get next line command is very simple, almost exactly the same as the Enterprise. The screen is 256 pixels across, 2 pixels per byte, so it's 128 bytes. So we add 80, which is 128. If we've gone over the limit of what L can store, then we just ink H, because the next line is directly below anyway. And that's all we have to do to get our screen locations. Very, very simple. Unfortunately, as I've already said, we do have some problems when it comes to actually getting the screen set up. And once again, just to reiterate, please make sure you've got interrupts disabled or throughout this tutorial, unless you're going to turn the ROM back on, because otherwise the ROM interrupt handler will execute part of the screen and you'll have a bad day there. So the first thing we're doing here is we're telling the system where its screen memory is. Now the port 252 defines the screen memory, and you can see here a description of the layout here, and all we're doing is we're telling it well, the screen memory is in page 2. That's what we're telling it here, and then down here and that's what these bytes are doing here. So now these top 2 bytes here, these are defining the screen mode, and we're using screen mode 4, which is basically the best screen mode, shall we say. It's the 16 color one. It's the only one I'm going to cover, because really I think if you've got a system this powerful and you're choosing to use it in Spectrum emulation mode, I think that's a bit of a mistake. So we're only going to be covering the 16 color screen mode in this tutorial. So we're selecting screen mode 4 here. We're telling the system it's in bank 2 here, and then we're sending all of that to port 252, which handles the video memory, and that will tell the hardware where the memory is. But now we need to actually make the memory accessible to the Z80 as well. So we tell the system to turn off the ROM with this bit 1 here, which as you can see, it says it replaces the ROM with RAM, and that's what we need to do here. And then we page in bank 2, which is the one we've just told the display to show from, and then that will do us there. Now because we've moved the lower memory, and that's where the stack pointer was, we have had to do a bit of a trick here. We're now moving the stack pointer so it will be in screen memory, and that's something quite important to note. If in this example the stack pointer is being put in a place that if you do switch off the lower bank, if you paged in a different bank into the lower area, you would cause problems. Turning the ROM back on will be fine, but if you switch to different bank in, you would cause some problems there. So we're popping the return address here. We're pushing it back here after we've set the new stack pointer in basically the screen buffer. And for this example, that will work just fine. So there we go. I mean, not too much of an exciting lesson this week, to be honest. Despite the differences in the screen layout, and there's quite considerable differences between the Spectrum and the SAM Coupe, the code is almost identical. When it comes to the bitmap data, as you see, this top bitmap, which is the raw bitmap data being sent straight to the screen, looks completely different, and that's almost intentional. And what we're going to look at later is I'm going to provide you the source code and the usable program of my sprite editor, which is the program I use for converting my graphics data for Chibi Akumas, and you'll be able to use it for making your own sprites and things, and using them with this code, or for anything else you want for that matter. So we're going to import a bitmap into that and export it in the Spectrum format and the Amstrad format and the SAM Coupe format, and we're going to let that program do all the work rather than trying to make assembly do it. So yeah, please bear with me on the rather limited functionality of these examples, but I can assure you, I think you're going to quickly see that although they're simple, we're looking at good content here, and it will really sort of pad out into something quite impressive quite quickly. Well, I hope you've enjoyed today's lesson. It's probably a little bit faster than the average one, but if you have, please follow on. So next week we're going to have a look at the MSX and the TI-83 calculator. Now, unlike the current systems we've looked at, those systems actually have a separate device that does the graphics work for us. So rather than accessing bits of memory and just poking the bitmap data in we want, we have to liaise with that device and make requests on the area we want to write to, and then send the data to it. So it'll be quite different to what you've seen today, and I would strongly urge you, even if you're not interested in either of those systems, it's worth having a look at them just to sort of prepare yourself for all eventualities of other systems we're going to look at later, for example, like the Game Gear or the Game Boy. Now, the Game Gear is also a system where you have to send data to an external device. So even if you're not interested in the MSX and the TI, please follow along, because I think you're going to find some interesting stuff there. Anyway, I hope you've enjoyed this lesson. As always, the source codes we've looked at today is going to be available on my website for you to download, and there is, as always, documentation of how it all works, which we've actually looked at a little bit today. But go ahead and look at it at your leisure, and I hope you'll find some interesting stuff in today's lesson. Thanks for watching, and goodbye.